So in this video we're going to investigate whether sine of n or cosine of n converge or diverge. And what we're interested in is as n approaches infinity. So that is what we're interested in. So we're going to do this in terms of sequences. So we'll let one sequence, a subscript n, be sine of n, and b subscript n be the cosine function of n. Now these are very similar properties, although different values are different values of n. So if I just draw the sine function first, so draw this on a graph. So the sine function starts at 0, and at pi over 2 it becomes 1. So I'll have that as my plus 1. So we'll follow this pattern, and then back down to 0 at pi, and we come back down to its minimum, which is minus 1 at 3 pi over 2. So if I mark that on my graph here, so that will go there. So we then come down to this point, and then back up to 0 again at 2 pi. And then follow the same sequence of pattern every 2 pi. So it's period 2 pi for the sine function. So that would be my sine of x. Now the cosine function is the same, except it's just shifted back pi over 2. So basically that would just follow down this way and follow the same sequence, just pi over 2 behind on the graph. So that's how the cosine function will work. So our sequences here are a of n equals sine of n and b of n equals cosine of n. Now what we have here, we have to find our maximum and our minimum to see if these two functions converge or diverge or not. Now sine of n, what we know is that the maximum of sine of n, so the maximum of sine of n, that equals 1. So sine of n equals 1 at 2 pi n plus pi over 2. So that's at 2 pi n plus pi over 2. And it reaches its minimum. So the minimum of sine of n equals minus 1. So this is positive 1 here, so let's not get these mixed up. At 2 pi n plus 3 pi over 2. So where n is an integer, so n is an integer, and it's a positive integer. Okay, so that's our minimums and our maximums. So how do we know if this converges or diverges? Well, by the Monotone Convergence Theorem, so MTC, I'll just write that as MTC, the Monotone Convergence Theorem, a sequence converges if it approaches one limit. So basically, for example, a function, if we have this as our function and the sequence follows this kind of pattern and it approaches a value along its sequence which is equal to L. So that will be our limit. So this, if it's strictly increasing, then and it's approaching L but doesn't go past L, then we can say this converges by the Monotone Convergence Theorem. Now our sine function does this, so it comes up like this and it reaches its limit and then comes back down again and then back up again. Now for it to be a sequence that's valid by the Monotone Convergence Theorem, it must be always increasing. Now the sine function is not always increasing. So this would not be valid under the Monotone Convergence Theorem, as would cosine either. Now another way we could look at this is if we take this term here, minus 1 to the n. Now for every n in this, our sequence, so if we call this sequence, for example, c of n, that equals minus 1 to the n, our values for this will become minus 1, 1, minus 1, 1, minus 1. Okay, so that's our sequence there, c of n. Now you can see here c of n, it goes from minus 1 to 1 to minus 1 to 1 to minus 1. So basically there's two subsequences here. So for odd values of n, so basically when n equals 2 k minus 1, where k is an integer, c of n equals minus 1. Now for even values of n, so even values of n, so that is when n equals 2k, so the even numbers, c of n equals 1. So therefore we could say by the monotone subsequence theorem, so the monotone subsequence theorem, we can say that this sequence here is divergent because it has two different limits. So we've got a minus 1 and a plus 1. So we can say by the monotone subsequence theorem, this sequence here is divergent. So I'm going to write here diverges. Okay, so this sequence here diverges. Now if we go back to our maximum and our minimum of our sine sequence, so a of n and b of n, sine and cosine behaving very similar, we can also conclude that sine of n and cosine of n also diverge. So these two sequences have different limits and are not increasing all the time. They are increasing and decreasing, so they're not strictly increasing either. So therefore we can confirm by many parts of the theorem that these two sequences do not converge, they diverge. So this one diverges, and so does this one. Okay.